When stars much larger than our Sun reach the end of their life cycle, they often die in spectacular explosions called supernovae. These cosmic detonations are among the most energetic events in the universe, releasing an immense amount of energy and ejecting the outer layers of the star into space. What's left behind after a supernova is often an incredibly dense core known as a neutron star. To get a clearer picture of just how extraordinary these remnants are, imagine cramming the mass of our Sun into a sphere no larger than a small city, roughly 10 to 20 kilometers in diameter. That's about the size of a city block, yet it contains the equivalent of roughly 1.4 times the mass of the Sun, sometimes even more. This means the matter making up a neutron star is compressed to an astonishing degree, so dense that a sugar cube-sized amount would weigh about 1 billion tons on Earth. This staggering density results from the collapse of the star's core during the supernova explosion. Normally, atomic nuclei are kept apart by electromagnetic forces. However, in a neutron star, gravity is so intense that electrons combine with protons to produce neutrons, leading to a ball of nearly pure neutron matter. This process is what gives the neutron star its name. Imagine squeezing a star until it's the size of a city, and what you get is a volume so small yet so massive that its gravity warps spacetime around it quite profoundly. To understand just how intense this gravity is, consider that if you could stand on the surface of a neutron star, which is impossible in practice, due to the crushing gravity, you would experience a gravitational pull about 100 billion times stronger than Earth's gravity. Gravity here doesn't just hold the star together, it influences every aspect of the neutron star's physical environment. Orbits around neutron stars are affected profoundly, and the star's own structure must withstand immense gravitational forces. This intense pull causes spacetime itself to curve sharply, a phenomenon predicted by Einstein's theory of general relativity. Light escaping from such a gravitational field is significantly bent and redshifted, stretched out to longer, redder wavelengths, a unique signature astronomers can detect with specialized telescopes. Beyond gravity, neutron stars are also known for their extraordinary magnetic fields. In fact, their magnetic strength can be trillions of times greater than Earth's. To put it into perspective, the strongest man-made magnetic fields created in laboratories reach only a few 100,000 times the strength of Earth's magnetic field. In stark contrast, some neutron stars, called magnetars, possess magnetic fields so powerful that they can distort the shape of atoms themselves, or even cause the star's crust to crack, or emit violent bursts of high-energy radiation. These magnetic fields are generated by the rapid rotation and convective motions within the star as it cools and contracts after the supernova. The result is a magnetic field of such strength that it can influence particle trajectories across vast distances, generating beams and emissions that we detect as pulsating signals. This leads us to a fascinating class of neutron stars known as pulsars. Pulsars are neutron stars that emit beams of electromagnetic radiation out of their magnetic poles. Because these magnetic axes are typically misaligned with the star's rotational axis, these beams sweep across space much like lighthouse lamps. When Earth happens to be positioned in the path of these beams, we observe regular pulses of radiation, hence the name pulsar. These pulses are incredibly consistent, sometimes matching the accuracy of atomic clocks, and they serve as natural cosmic beacons that tell astronomers a great deal about the star's properties and behavior. Pulsars are essentially the universe's most precise clocks, and their discovery in 1967 was a milestone in astrophysics. Their study has shed light on exotic physics, such as how matter behaves under extreme densities and magnetic fields, and has even helped confirm Einstein's theories of relativity. The regularity of pulsar signals provides a means to measure distances, test gravitational theory, and explore the fundamental nature of matter and energy. Another remarkable aspect of neutron stars is how their magnetic fields size up against their rapid rotation. Many neutron stars spin hundreds of times per second, completing a full rotation in mere milliseconds. These are called millisecond pulsars, and they owe this rapid spin to their interactions with surrounding matter. Often they are part of a binary system, orbiting a companion star. And as matter from the companion falls onto the neutron star, it transfers angular momentum. This spin-up process results in an incredibly fast rotation, which amplifies the star's magnetic field and makes the pulsar beams even more precise. This combination of intense gravity, ultra-strong magnetic fields, and rapid rotation creates a variety of phenomena that are both fascinating and complex. For instance, magnetars, which are a subset of neutron stars with even more powerful magnetic fields, can produce dramatic bursts of high-energy radiation called soft gamma repeaters, sometimes releasing as much energy in a fraction of a second as the sun does in hundreds of thousands of years. These bursts are believed to result from the star's magnetic field reconfiguring violently, cracking the crust, or starquakes, similar to earthquakes, but far more energetic. Despite their small size, neutron stars have a profound impact on their surroundings. Their intense magnetic fields and radiation can influence nearby space and even affect the interstellar medium, the gas and dust that fills the space between stars. The high-energy particles accelerated by their magnetic fields can contribute to cosmic rays, which are energetic particles that travel through space and occasionally reach Earth, impacting our atmosphere and environmental conditions. One of the most intriguing features of neutron stars, especially pulsars, is their stability and longevity. These objects can emit beams that sweep past Earth for millions or even billions of years before they slow down or decay, providing astronomers with a long-term window into their complex physics. Their consistent pulsing allows researchers to probe the environment surrounding them and study the fundamental laws of physics under conditions that cannot be recreated in laboratories. In summary, neutron stars are extraordinary entities born from the death throes of massive stars. Their matter is compressed to such an extreme degree that it defies our everyday understanding of density and gravity. Their magnetic fields rival the strength of any magnetic phenomenon observed elsewhere in nature, and their rapid spins turn them into cosmic lighthouses known as pulsars. These stellar remnants offer invaluable insights into the universe's most fundamental physical principles, and continue to captivate scientists with their mysterious and powerful nature. Through studying these remnants of stellar death, we better understand the cosmic cycle of creation and destruction, the behavior of matter under extreme conditions, and the interconnectedness of cosmic phenomena that shape our universe. One of the most astounding aspects of neutron stars is just how incredibly dense they are. To picture this, consider the familiar object of a city. A typical large city like New York or Tokyo covers hundreds of square miles, packed densely with buildings, streets, parks, and millions of people. Now imagine squeezing all that into a sphere with a diameter of only about 20 kilometers, roughly the size of a small city or a large town. That's approximately the size of a neutron star. Yet despite their small size, these objects contain a mass greater than that of our Sun. To put that into perspective, while the Sun weighs about 2 nonillion tons, that's 2 followed by 30 zeros, a neutron star of similar mass packs it all into a space just a dozen miles across. The result is a sphere where a teaspoon of neutron star material would weigh about 1 billion tons, equivalent to the weight of a mountain on Earth crammed into a tiny atomic-scale volume. But how does matter become so incredibly dense? To answer this, we need to understand what happens when a massive star reaches the end of its life. Stars are essentially colossal nuclear reactors, fusing lighter elements into heavier ones to release energy that counteracts the force of gravity pulling everything inward. When a massive star exhausts its fuel, gravity begins to dominate. The core collapses under its own weight, crushing the atoms together. Instead of electrons and protons being separate, they merge to form neutrons, a process called neutronization. The result is an object comprised almost entirely of densely packed neutrons, which is what we call a neutron star. This collapse is so extreme that it raises the question: what prevents the star from collapsing further into a black hole? That's where the physics of neutron degeneracy pressure comes into play. Similar to how electrons resist compression in white dwarf stars, neutrons also exert a quantum mechanical pressure against further collapse. In simple terms, the Pauli exclusion principle states that no two neutrons can occupy the same quantum state at the same time. This creates a kind of quantum pressure that resists gravity. Yet despite this pressure, neutron stars are still barely holding themselves up. If the mass of the collapsing core exceeds about 2.1 times that of the Sun, the neutron degeneracy pressure won't be enough, and the star will continue collapsing into a black hole. The conditions inside these stars are truly extreme. The density is so high that a single teaspoon of neutron star material would contain as many neutrons as all the grains of sand on Earth. The temperature of a neutron star's interior can reach billions of degrees, hot enough to emit intense X-ray and gamma-ray radiation, which is why some neutron stars are observable across the universe. Their magnetic fields are mind-bogglingly strong, trillions of times stronger than the magnetic field of Earth. To put that into context, if you could somehow place a magnet with the strength of a neutron star's magnetic field on Earth, it could strip away everything metallic and induce electric currents in the atmosphere, disrupting communications and satellite operations. The rapid spins of neutron stars add a further layer of fascination. When a star undergoes a supernova explosion, the massive outpouring of energy marking its death, the remnant core initially may rotate relatively slowly. However, if the star interacts with material from a nearby companion, or if conservation of angular momentum causes it to spin faster as it shrinks, the neutron star can end up spinning hundreds of times per second. These are known as millisecond pulsars, and their rotation rates are mind-boggling compared to your average spinning top. This rapid rotation is crucial because it amplifies the star's magnetic field, producing powerful beams of radiation emanating from the magnetic poles. If these beams sweep past Earth, we detect them as precise pulses of radio waves or X-rays, hence the name pulsar. Imagine a lighthouse with a beam sweeping across the horizon, except in this case, the lighthouse is a tiny city-sized object spinning hundreds of times per second, and the beam is a narrow jet of electromagnetic radiation. Because of the extreme stability of these rotations, pulsars have become some of the universe's most accurate natural clocks. They enable scientists to conduct precise tests of fundamental physics, including Einstein's theory of general relativity. For example, observing pulsars in binary systems, where two stars orbit each other, has been instrumental in confirming that gravitational waves, ripples in space-time, exist, as predicted by Einstein. Some neutron stars, called magnetars, push the limits even further. These are neutron stars with magnetic fields so intense, more than a quadrillion times stronger than Earth's magnetic field, that they can produce violent bursts of gamma rays and X-rays. These bursts, known as soft gamma repeaters, can release as much energy in a fraction of a second as the Sun will emit over hundreds of thousands of years. The intense magnetic stress can cause the crust of the star to crack, generating a starquake, a kind of cosmic earthquake. These reconfigurations of magnetic fields can lead to sudden, powerful emissions of radiation, often observed as intense flashes or flares. The impact of neutron stars isn't confined to their immediate surroundings. Their magnetic fields and energetic radiation influence the space around them, shaping the environment of the interstellar medium, the gas and dust that fills the universe between stars. Charged particles accelerated by the fields of pulsars and magnetars contribute to cosmic rays, high-energy particles that travel through space. Occasionally, these particles reach Earth and interact with our atmosphere, contributing to phenomena like auroras or even affecting satellite and airline operations. Despite their small size, neutron stars can shine brightly in the sky, mainly in X-ray or radio wavelengths, and can be observed across great distances. Their stability over millions or even billions of years allows astronomers to use their regular pulses to map out the universe, measure cosmic distances, and study the behavior of matter under conditions impossible to recreate on Earth. All these extraordinary features come together to make neutron stars some of the most intriguing objects in the cosmos. Their formation is the final act in the life of a massive star, and their existence provides scientists with natural laboratories for probing the laws of physics under conditions that push matter to its absolute limits. Studying these stellar remnants not only helps us understand stellar evolution, but also opens windows into the fundamental nature of matter, gravity, and the universe itself. The way they cram so much mass into such a tiny volume challenges our understanding of physics and continues to inspire curiosity about the universe's hidden depths. As research advances, we are beginning to see neutron stars as cosmic classrooms, places where the extreme teaches us lessons that reach far beyond astrophysics, touching upon the very fabric of reality. One of the most remarkable aspects of neutron stars is how they exemplify the extraordinary states of matter that can exist under extreme pressure and density. At the core of a neutron star, matter is compressed to a point where electrons and protons are fused into neutrons, creating a substance known as neutron-degenerate matter. Unlike anything else we encounter on Earth, this form of matter is so dense that a sugar cube-sized amount would weigh about 1 billion tons on our planet, roughly equivalent to the weight of a small mountain compressed into a tiny space. To put it into perspective, the entire mass of the Sun squeezed into a sphere just about 20 kilometers across, roughly the size of a large city. Yet packed into that small volume, the pressure and density are so immense that our conventional understanding of physics is pushed to the limit. The pressure inside a neutron star is so intense that it halts the natural tendency of matter to collapse further, balancing gravity with quantum mechanical effects. This quantum pressure arises from the Pauli exclusion principle, which states that two fermions, particles like neutrons, cannot occupy the same quantum state simultaneously. Under ordinary circumstances, this principle prevents matter from compressing infinitely. In a neutron star, however, this quantum resistance is stretched to its maximum, holding the star up against gravity's relentless squeeze. This delicate balance forms a kind of cosmic tension, where the forces of quantum physics and gravity are locked in an incredibly dense equilibrium. Understanding how this balance works is fundamental to nuclear physics, because neutron stars are natural laboratories for studying matter at densities that cannot be replicated elsewhere. An interesting facet of neutron stars is that their extreme densities lead to unusual properties of their own. For example, the liquid interior of a neutron star is thought to behave like an almost frictionless superfluid. Superfluidity is a state of matter in which fluids flow without viscosity or resistance, a phenomenon observed in laboratory experiments with liquid helium at ultra-cold temperatures. Inside neutron stars, however, this superfluid state exists in a realm far beyond ordinary physics. It occurs at hot temperatures in cosmic terms, but supercooling in terms of quantum phenomena. This superfluid core influences how the star rotates and can be responsible for sudden changes called glitches, where the pulsar's rotation rate abruptly speeds up due to the decoupling and recoupling of the superfluid interior with the star's crust. These glitches serve as clues to unravel the complex inner physics of neutron stars, offering a glimpse into the behavior of matter under extraordinary conditions. The intense magnetic fields of neutron stars also play a crucial role in shaping their observational features. In fact, the magnetic field strength of typical pulsars is around 1 trillion times that of Earth's magnetic field, and in magnetars, it can reach magnitudes so enormous that they distort the structure of molecules and atoms on a microscopic scale. Such magnetic fields are generated during the star's collapse when the core's magnetic flux becomes concentrated as the star shrinks in size. The result is a magnetic field that influences not just how the neutron star radiates, but also how it interacts with its surroundings. When magnetic field lines twist and reconnect, a process similar to what occurs during solar flares, it can release tremendous amounts of energy, leading to sudden bursts of high-energy radiation. These flares can outshine entire galaxies for brief moments, providing astronomers with dramatic signals that encode information about the star's magnetic properties and internal structure. Not all neutron stars are equally active, however. Many have become comparatively quiet over time, gradually losing their rotational energy and magnetic activity. Still, the ones that are active offer critical insights. For example, the precise timing of pulsar signals allows scientists to use these stars as cosmic clocks that are remarkably more stable than any mechanical clock designed on Earth. Such stability originates from the remarkable uniformity of the neutron star's rotation and its consistent emission of pulses. This makes pulsars invaluable tools for testing the fundamental laws of physics. For instance, by monitoring 2 neutron stars in a binary system, a pair orbiting each other in a cosmic dance, researchers have confirmed the existence of gravitational waves, the ripples in spacetime predicted by Einstein's theory of general relativity. These observations, made with pulsars, predate the direct detections made by gravitational wave observatories like LIGO, and they continue to refine our understanding of gravity's behavior in strong field conditions. From a broader perspective, neutron stars influence their surroundings in more ways than just their immediate electromagnetic emissions. Their energetic particles, cosmic rays, permeate the galaxy and sometimes make their way to Earth, impacting our environment. These high-energy particles can ionize atoms in Earth's atmosphere, leading to phenomena such as auroras, or interfere with satellites and communication systems. Understanding how neutron stars accelerate particles to such energies offers insights into cosmic ray origins and the energetic processes occurring in our galaxy. Moreover, some neutron stars are part of more complex systems, binary pairs, or even multiple star systems, that serve as natural laboratories for studying stellar evolution, black hole formation, and the life cycle of matter in the universe. Despite their small size, neutron stars are visible across vast cosmic distances primarily through X-ray and radio observations. Their compactness and the regularity of their pulses make them some of the most precise beacons in the universe. These signals have helped map out the distribution of matter in our galaxy and distant galaxies, estimate cosmic distances, and probe the properties of space itself. For example, by studying the timing and frequency of pulsar signals, astronomers can detect tiny irregularities caused by the gravitational influence of other objects, sometimes revealing the presence of planets orbiting these stars, or showing the influence of dark matter in unseen regions of space. As research progresses, scientists continue to uncover new types of neutron stars, some with even more extreme properties than previously imagined. For example, recent discoveries suggest that neutron stars can exhibit behaviors that blur the lines between pulsars and magnetars, challenging traditional classifications. Theoretical models are increasingly sophisticated, incorporating the principles of quantum mechanics, relativity, and nuclear physics to understand these exotic objects. Advanced telescopes, both ground-based and spaceborne, are allowing astronomers to observe neutron stars across the electromagnetic spectrum with unprecedented precision, revealing details about their interiors, magnetic fields, and emission mechanisms. The study of neutron stars also intersects with some of the most fundamental questions in physics. They offer real-world environments where matter is compressed to densities that cannot be achieved in laboratories on Earth, providing potential clues about the behavior of quarks, the fundamental constituents of protons and neutrons, under extreme conditions. Physicists are eager to understand whether the core of a neutron star might contain even more exotic forms of matter, possibly including a phase called quark-gluon plasma, or whether it might harbor a hypothesized state called a strange quark matter, a theorized form that could be more stable than ordinary nuclear matter. In essence, neutron stars serve as bridge objects, connecting astrophysics, nuclear physics, quantum mechanics, and general relativity. Their extreme environments challenge our understanding of the universe's fundamental laws and push scientists to develop new theories and models. The ongoing exploration of these cosmic remnants continues to surprise and enlighten us, revealing the incredible resilience and diversity of matter under conditions that are as perplexing as they are fascinating. In contemplating these compact objects, we are reminded of the profound interconnectedness of the cosmos, how dying stars leave behind remnants that become laboratories for physics, how these remnants influence their surroundings, and how studying them ultimately helps us understand the origins and evolution of everything around us. Neutron stars, tiny yet monumental in cosmic terms, are emblematic of the universe's capacity for extremes, holding within them the key to some of the deepest mysteries of nature. As technology advances and our observations sharpen, the secrets of these stellar titans will continue to unfold, offering insights that may forever reshape our understanding of the fabric of reality itself.